I wanted to thank Jeremy for doing this presentation on rare earth elements mining. Brief introduction that you can find on our website. Dr. Jeremy Williams is a geoscientist who utilizes geochemical and geophysical techniques to understand the fluid migration of unconventional oil and gas reservoirs, investigate the role of redox conditions and mineral resources, and understand the significance of acid-base reactions and their environmental effects. He was an assistant professor at the Department of Geology at Kent State University, among other things. The reason I invited Jeremy to do this, and I'm so pleased that he agreed, is because he has one of the better understandings, not only of the geological implications of rare earth element mining, but also what that means for the climate and what that means for human beings.
Today, what I'm going to talk to you about is the truth about rare earth element mining, and also what are rare earth elements, what are they mined for, the implications behind them, and also human health effects that are related to rare earth elements and mining. A little bit about, like Deb said, I used to be an assistant professor at Kent State University. I now work for Thermo Fisher Scientific as an application scientist in their what we call the bulk elemental analysis division. Essentially, I work with a lot of people who are trying to look at rare earth elements and the context of where it comes into manufacturing. So, different manufacturing applications. Also, I work with a lot of different people all over the science realm, whether it's cement applications, anything to do with geological material, those applications, super alloy metals, as well as cast iron. So pretty much every single thing in your house that is an appliance or has is a non-living thing. That's I work with those companies, glass companies, and I also work with pharmaceuticals as well. So I pretty much work with everybody at the moment, and um, I know I've kind of crossed over into the dark side of being on the industry side, but I like it because you still get to influence people on how to do things in a sustainable way. And so that is one thing that I truly like about it because I'm actually engaging with a lot of people who are high school educated. I know Deb said that you aren't political, but I engage with a lot of people that voted for the president. Like I engage with them. That's probably my biggest customer base. So it helps to understand and also talk to them and then see where they're coming from as well. So one of the things that I used to always tell my students is that any energy source, whether it is oil and gas, hydro, nuclear, wind, solar, or green, comes with a cost. So one of the biggest things that the president said that got a lot, this was back in when his first term, where he said that wind energy is killing the birds, like they're flying into wind turbines. And he wasn't wrong about it, but it just came across so funny when he said it. But there are also that is like an actual concern. So when it comes to all sorts of energy sources, we have to be concerned with the cost no matter what. Like every single thing comes with a cost. Just because it is green energy, that does not mean it is taken from oil and gas. It's taking oil and gas to make it. It's not taking mining sources or other mineral sources to make green energy. And so everything is going to come at a cost. And we're just going to talk about rare earth elements today. So what are rare earth elements? Rare earth elements are they're referred to the sorry, let me put my screen down. They're referred to the seeds of technology. Their significance in national security and high-tech products. So your cell phone, the computers that we're on, our TVs, almost a lot of almost every single electronic has some form of rare earth elements in them. China is the largest producer. It's about 90% of the world's production. I want to get into why that's the case. And they aren't necessarily rare. The thing is that they're rare in enormous amount of concentrated material. So you can find rare earth elements everywhere. They're just not concentrated, but only in specific areas. And I'll talk about where you find those at as well. If you see the highlighted red, this is a periodic table. This is the Goldschmidt classifications. I'm going to teach you a quick session about how to look at geology or look at the periodic table in the context of the Earth. So Goldschmidt was created by an ore geologist back in like the 1920s. And so what he did is that he said that elements on Earth are going to be clumped in two areas. They're going to be clumped with silicates, they're going to be clumped with sulfur, or they're going to be clumped with iron. Silicates are going to be your rock forming. So these are going to be what we call your lithophiles. So that we call them rock loving. So if we think about the continental crust, we have sodium associated with magnesium, aluminum, phosphorus, potassium, calcium, and so forth. When we talk about siderophiles, these are iron loving. So these are going to be in red, and you'll see some of them they could be both a siderophile or a lithophile or what we call a chalcophile. They can behave in the same, or I would say they can have similar properties, and it's just because of changes in the environment. These are going to be iron loving, so that means that they're going to be associated with iron. They have a high affinity for iron. So when we talk about nickel, nickel is oftentimes associated with iron when we look at ore body material. And the last thing is chalcophiles. These are sulfur loving. So copper, when we talk about harnessing or getting copper, precious metals like silver, when we talk about palladium, these are different elements that are going to be in sulfur ore bodies. So they have a high affinity for sulfur. So whenever you're going out, whenever people are going out and mining, they're really looking for ore bodies associated with silicates, iron, and sulfur. That's the gist of how the periodic table works with the Goldschmidt mine. And then the last one we have are atmophiles. So these are like hydrogen, helium, carbon, nitrogen. These are gas loving. So when we talk about CO2 emissions, carbon likes to be in the CO2 phase more so than the solid phase. And because of that, that's why we have greenhouse gas. That's why we're so concerned about CO2 is because carbon has an affinity for being in the gas phase. So generally speaking, when it comes to rare earth elements, there are a total of approximately like 13 of them, and we can find them in different places. So we can find them in your electronics, medical applications. So if you ever got an MRI, an X-ray, you can find it there. You can find it in magnets and motors. So your car contains rare earth elements. Energy storage, like batteries, they contain rare earth elements. Your light bulbs, and also catalysts. So any type of catalyst, we see catalysts with oil and gas. So they use rare earth elements to hinder from your car pretty much giving off more emissions than it should. And so these things are like you can see that they have a very, very wide application use. And the distribution of them, like I said, they're not rare because this is the distribution of our solar system or of our planet. So our solar system and our planet are pretty much the same in distribution, quote unquote. But if we look at, well, let me go back and say our planet has a different distribution, but it's somewhat similar to the solar system. So when we look at our planet, we have our rock forming elements. As you can see, these are going to be the more dominant major elements of the continent or of the earth. And then when we look at the rare earth elements that are in blue, you notice they're not that rare, but the rarest of them all is our precious metals like osmium, platinum, gold, iridium. Uh, right now we're starting to see in my area of work, I'm starting to see more people wanting to look at gold, or they want gold because of the price of gold has gone up. So this is what we see when it comes to the rare earth elements. So they're not rare, they're just like I said, we see them everywhere. They're concentrated in special areas. When we look at the actual reserve, the highest concentration is going to be China. China is the highest concentration, followed by Vietnam, Brazil, USA, Russia, India, Australia, Greenland, Tanzania, Canada, and South Africa. So notice that these are the countries, and then when we talk about the rest of the world, it's about like point, it's about like 1% the rest of the world. When we talk about quantities and major processes that are going on with rare earth elements, you're going to have China, United States, Australia, and Myanmar are going to be the biggest ones. China is globally the most, China has the stranglehold on the market when it comes to rare earth elements. So 70 to 90% of it. And if you are into geopolitics when it comes to the pressure, you notice that probably the pressure was put on China, or you start to hear politicians talk about China in a way, in a derogatory way with natural resources around 2010, because China put a constraint on why they were producing rare earth elements. Sometimes you have to take certain things with a grain of salt. This is coming from Chen et al. He's basically saying, or they're basically saying that taxes, quotas, licensing, as well as preserving their rare earth element resources to meet the domestic demand more so than environmental concerns is the reason why. And then China also knows that we have the biggest market on it. We're starting to see an increase in rare earth element uses. So therefore, we're going to clamp down. They're not the only ones. The United States does it too. The United States has the control of helium. So we control helium prices. Helium is used for defense. So when you go through TSA security, when you get also medical applications like uh, MRIs, X-rays, they're using helium sources. And those helium sources are coming from natural gas sources. That's how we get helium. And the shortage of helium is because, like, once you use it, it goes into the atmosphere and you can't grab it. So you have to harness it from natural gas or oil and gas fields. And then, so when China began to clamp down on rare earth elements, other countries began to say, let's start conserving or recycling our materials so that way that we can have our own reserve. So one of the things when Biden had passed the CHIPS Act, it did place a heavy emphasis on recycling materials, and that was with rare earth elements. In fact, when you saw that legislation go into effect, we saw a lot of startup companies that were into green technology that were recycling material. So they were constantly thinking about recycling uh, your electronics. So that really exploded during that time. You don't see it now because of the new administration that's in effect. When it comes to rare earth elements, they're in the news. So we know that the president wanted to get Ukraine to do a deal that didn't work out, and this deal was to obtain rare earth elements. So the administration knows about them. The people that are in the cabinet position seek to gain from rare earth elements because they have such a high investment in them. We see that it's also sparked trade wars. It's probably we you hear about soybeans, you hear about these other things, but really behind a lot of the the conflict between the United States and China, or China and other countries, is because of the rare earth elements. They're also an environmental disaster, so we're going to get into why that's the case. And yeah, it and then with with the president wanting to take Greenland or when doing these certain things like Venezuela, there are reasons why because they also have rare earth element reserves. So you start to put two and two together as to why these different things are. And again, his family also seeks to benefit from rare earth elements because they do have investments in them. When we talk about rare earth elements are going to be in, let's say, the when we talk about the global perspective, they're what we call carbonatite related deposits, so volcanic deposits, deposits from alkaline igneous rocks. So once again, magmatic hydrothermal vents, these are all related to volcanic activity, residual weather deposits, placer deposits, and offshore sedimentary deposits, and also in coal. And this diagram that I'm showing you is where the rare earth elements are. These are the mining sources, and these are the different types where we find them at. So they're mainly associated with volcanic activity. Like I said, you're starting to see Greenland, you have Canada, you're starting to see China. So you see they're kind of clumped in different areas. So why is that the case? Well, when we look at the actual environment or the climate, they're really occurring along, let's say, uh, sea or where we have or mountain belts along with being with river sources or water sources. So we see them along the Atlantic Ocean. We see them along the shores of India, China, Australia, and Madagascar and Tanzania. So we're starting to see where they are accumulating at. So if you are an oceanographer, you say to yourself, oh, wow, that looks like ocean currents. And if you're looking at it, you're absolutely right because the ocean currents are pretty much help dictating where we have these deposits being made at with the rare earth elements. So even though you do have some along the United States and we do have them in the inner part, but this is also weathering related. You see along China, you're starting to get the accumulation in this in the along, like I said, along the sea. One of the things about rare earth elements is that if I have a mantle plume and it goes through continental crust, that's going to be a sign for where I'm going to have rare earth elements accumulate at. So this picture where this is a sandstone and we had this phentonization of rare earth elements. So this is what we typically see. So they're going to be in rock formations and they're going to be in coal formations. So where I have intrusions of volcanic activity over millions of years is where I have it. Now, when I talk about, let's say, the subduction zone of the Pacific Ocean, I don't really find them there because that source of mantle plume is that source of, I would say, that volcanic source is not necessarily coming from the mantle. It's more shallow, it's more continental asthenosphere related. But the biggest thing that we see with rare earth elements is that typically when I have weathering events, and this is also going to be true when we talk about environmental impact of rare earth elements, meteoric water is going to leach out those rare earth elements. And then once they leach out, they're going to become ions and then they'll precipitate out again and then they'll be in different deposits. So you'll see they'll be in very what we call, we have it in the Oxbow Lake where it's in a meandering stream. That Oxbow Lake is cut off from the actual stream. And when that is cut off, it's low energy. So when it's low energy, I get to deposit these rare earth elements. So we find, and this is what's going on in China, is that we have these fluvial environments all along the Pacific Ocean on the Chinese coast, and we're having these effects of rare earth elements just accumulating. So this is the reason why. And also remember I said mountain building events, one of the biggest building events on the planet right now is the Himalayan mountain range and the Tibetan plateau. If we want to go into that from an environmental and a climate perspective, that's the reason why we had the Asian monsoon. So we're having all this weathering come on down, and then it's causing for what used to be volcanic activity from the Himalayan mountain range, because they were volcanoes at one point. They're cut off, but all of those deposits from rare earth elements are now being deposited along the coast. So if I just go back where we see with India, Myanmar, Vietnam, and China, this is, and you see the riverbeds that are going there, you do see that rare earth elements are where they're depositing at. Next, we can have it where we have coal. So when they combust coal, you're going to have rare earth elements, and then through an extraction phase, you're going to precipitate out rare earth elements. So fly ash coal, which is very dangerous to the environment, we do see that that's where we get our rare earth elements from, or we get to harness them from these sources. And as you can tell, like this requires a lot of energy, and it's also you're also releasing CO2, you're releasing sulfur dioxide, you're releasing a lot of greenhouse gases when you're combusting coal and the fly ash just to get rare earth elements. And the last one is hydrothermal vents. So hydrothermal vents, if we talk about the seafloor spreading center of the Atlantic Ocean, the Pacific Ocean, of all our oceans, you get these unique colors, and this is because of the it's sulfate reducing bacteria that's down here that's really driving the ecosystems. And so we have rare earth elements that are accumulated along the sea floor because they're coming out of the mantle, or they're coming out of the melt that's generated from the mantle. They're instantly getting cooled as they hit this water, and then they're being precipitated across the ocean floor. So I'm not going to go into this diagram too much, but basically you have these black smokers, and then they're releasing all of these compounds along with rare earth elements, and then they're just pretty much being accumulated on the ocean floor because it's an instant precipitation of rare earth elements, because it's coming out at like 400 degrees Celsius, and then it cools down to 2 degrees in a matter of seconds. The administration knows this. So what they're trying to do in this case is that they are trying to, and they're not doing it now because they're involved in everything else that's going on in the world and doing so, they're probably not concerned about their energy is spent elsewhere. But the administration has said that we want to do mining on the seabed to harness rare earth elements, so we don't have to worry about China or these other countries. That itself poses a lot of risk, because nobody's really done deep sea mining. We have done deep sea drilling for oil and gas, and that requires a lot of maintenance, a lot of energy, and it just requires a lot of monitoring, just a lot of energy for not blowing up the well when you're talking about oil and gas. And then as you're sinking down into going down to the seafloor, you have to worry about the pressure of the water and the temperature. So the pressure is the main thing. If anybody's a scuba diver, they know that you have to be mindful of the pressure. Like you can't go down deep pretty fast because that can crush. So it does that to also our machinery, our equipment. If we go down and start trying to harness these rare earth elements, it will be really hard to go down, grab, and then pull up, and then also you're changing the environment. And then you're damaging your equipment along the way because you have to account for the pressure that is associated with pulling that rare earth element. And so this is what you see on the ocean floor. You see these black nodules that are just littered on the ocean floor, and these are all rare earth elements. Like they contain a bunch of rare earth elements. And so this is what the administration wants to do, but they probably won't get to this because of everything else that's going on. And it requires a lot of resources. Not only does it require a lot of resources, it requires a lot of research and development that they took the funding away from. So they just can't, you just can't go down there and just grab it like an open pit mine. You actually have to think about how you're going to get down there, how you're going to pull it up without losing it. And will these structures or will these what we call these nodules change as they come to the surface because they're under pressure in this environment. Once we bring them to the surface, the pressure changes and therefore they might change as well. When we talk about rare earth element mining, it is not done sustainably. So you have water quality degradation. Not only do you have water quality degradation, you have toxic pollution and radioactive waste, air pollution, soil and habitat destruction, destruction of groundwater. So everything that you can think of with mining, everything that you can think of with climate change, these are the same things, but probably worse because now we're talking about radioactive waste. And the reason why we're having radioactive waste is because most of the time when we find rare earth elements deposits, you also find thorium and uranium concentrations because they occupy that same type of niche in the geological environment. And so this is a picture of a person in China that is actually at a rare earth element site where they're mining. And as you can see, if he is mining for rare earth elements, know that there's uranium, know that there's thorium there, not properly suited to handle this. And you could just see it is an open quarry like a limestone or a sandstone quarry. So these things, I mean, you drive past them, you won't know if you're looking at a rare earth element site or a cement site or a cement quarry site. And when we're mining these things, what's the biggest thing about it that is, I don't want to say it's worse than climate change like CO2 emissions, but it is probably worse. It's a simple fact that you're releasing toxic chemicals. And when we release these toxic chemicals, it takes a longer time for the environment to break them down. Also, we heard about the fact that recently with Iran, that black cloud and then it was raining oil. That's also happening because once these chemicals are being evaporated into the air and they're being rained down on, so therefore you're going to have those impacts. Also, there is no regulation when we talk about open pit mining or certain forms of mining. Basically, what they say is, okay, you do the open pit, they tell you to close up the area, but people go close up other areas and leave their areas open. So that's one of the things. We don't really have regulation, and regulation has decreased in the United States because a lot of our rare earth elements are going to be where our national parks are. And this is what open pit mining looks like. So as you can see, we're just taking off the top of a mountain and then you're digging it and then you're just slowly getting um, this out, like you're getting these rare earth elements out. And so when you're doing that, you're you're open to the atmosphere. Not only are you opening, so these structures have not been are not exposed to the atmosphere when they're formed, and when we expose them to the atmosphere, we have oxidation and chemical weathering going on. So the best type of example of oxidation and chemical weathering is when you see rust. Rust is, when if you leave some metal out and you have rust on it, that's iron now binding to oxygen because because of chemical weathering, it is now being exposed to a different environment. And so therefore, that's also happening with the structures that are no long that are now exposed when they were created by volcanic eruptions or volcanic melt. The biggest thing that we find is acid mine drainage. And so, acid mine drainage with rare earth elements, you find this a lot with coal, you find this everywhere. So, it's pretty much one size fits all when we talk about mining and rare earth elements, along with other environmental implications. It's just that now we're also talking about radioactive waste too. So, when we do have acid mine drainage, what's going on is that like I said, it's the same thing. You have what used to be bounded up and like sulfur, which was bounded up in pyrite or with iron. We see that a lot. It now is being oxidized by water. And then what's doing is being released into the environment. And there's no way to truly control this. They try to control it. They try to put, ponds to capture it before it leaches out, but it's also leaching out into your groundwater, which I'm going to talk about too. And so when it dissolves, it's coating your streams, it's lowering your pH. And once you lower the pH, you start to change the environment because a lot of things are pH tolerant. And so this can cause cancer related illnesses. You see a lot of acid mine drainage and people having illnesses associated with it. You find it a lot in the Appalachia area. Sorry. Other impacts that we see with rare earth elements, water consumption. They consume a lot of water. So water, like in South Africa, it's a really, you see it a lot because it's in a very arid environment. So it puts a damper or it puts strain on the water resources. Surface to groundwater contamination. That's everywhere. When I talked about acid mine drainage, once you start oxidizing groundwater, you're starting to trigger things that should not happen in groundwater. So you can trigger high iron concentrations, you can trigger high sulfate concentrations. So, and if people are ingesting this, they can then get sick. It can also affect the environment where it could affect your soil quality. It could start killing things. So that's one thing about it. You also have illegal mining going on. So, especially in Brazil and in South America, we have rare earth element mining in indigenous land. And like I said, it's associated with toxic and radioactive waste. And we do find where people have to move because of the fact that the radioactive waste from the rare earth element mine has pretty much polluted the land and they have to get up and move so they won't be exposed anymore. The discharge from rare earth element wastewater pollutes China resources. So when we talk about, I think I have a slide on this, but China's water is really polluted from rare earth element discharge and it's going into these urban environments. You also have recycling efforts. Although we do have recycling going on, it produces just as much waste, and there is a heavy consumption of energy when you are recycling these rare earth elements. So countries that are recycling, they also have heavy water consumption. It's producing large waste. You have to do something with that large waste. 9 times out of 10, it is also radioactive. So therefore, you have to dispose of it carefully. And then, like I said, I've been saying this a lot, radioactive waste, that's human health effects. That's the biggest thing that we're concerned with. And so when it comes to rare earth elements, they can affect your respiratory system because if you inhale it, you can start having pulmonary fibrosis, cardiovascular system. When we talk about lanthanum and neodymium, as those two rare earth elements, they can damage your DNA and you can pass it down, and then that can cause what they call it genotoxicity. That could cause you to have your offspring and your descendants to deal with the consequences. reproductive health. It can affect your reproductive health. It can trigger osteoporosis from your skeletal system and also digestion system. So pretty much everything these rare earth, it's just dependent on which one you're exposed to. And they all, even though they're clumped in a class, they behave differently in nature. And hence why you might have some that affect your respiratory system if you're exposed to it, or it might affect your skeletal system. You can also have, we also see cancer-related illnesses with rare earth elements. You can also have genotoxicity from bioaccumulation. So the same thing that we see with mercury, where they tell pregnant women not to eat mercury because it could damage their baby. That's the same thing, but that now it's damaging your DNA and you're passing it down. So these are some of the human related effects that we see with rare earth elements. So once again, it poses a question. Um, when we do this, when we use this type of technology, or we're harnessing these resources, at what cost? Because a lot of this stuff is not regulated. And so I did send this in the notes. This is, I think you all will have a nice time reading this, but it talks about how rare earth elements are impacting civilization, impacting people around the world, and they're also causing conflict. So, like in Myanmar, you have protesters and they're doing execution of protesters that are talking about, hey, we don't want this mine, or we want you to regulate it. They're prosecuting people out there, and the same in China. And then when we talk about China, you also have like the Yellow River, which is a big tributary in China, and it's affecting drinking water, fishing, and industry. So these people are being exposed to all of these toxins because there isn't a large regulation. And also, when you think about it, because rare earth elements are concentrated in certain areas, they're not getting that attention. With that being said, that is the end of my presentation.
I wanted to contextualize this. We're coming up on Pesach, Passover, and I wanted us to reframe that this year um, in a climate justice context. And that was a big part of why I thought it was important to have Jeremy come and talk around this time of year, because I think the connection is clear. Pesach, to some extent, deals with issues around resource extraction and the bad ways in which that was handled. And I think that rare earth element uh, extraction is a kind of really serious modern day version of that. But I wasn't expecting so much radioactivity. I'm just going to say that.
You mentioned the national parks. Can you talk more about that?
Yes, they are. A
National
lot of our national parks are in mountainous areas, mountainous terrain. And when we talk about Yellowstone, we talk about all these different national parks. They're I'm not trying to say they're unique ecosystems, but they are what we call orogenic events. So we're talking about mountain building events, which is classic for a lot of different metals, a lot of different precious metals, not only precious metals, rare earth elements, all of your oil and gas is out there, and this is untouched. So the administration, for instance, wants to go out there and do something about it. Also, I didn't talk about it, carbon capturing. That's kind of on the back burner now, but that's the idea of what they want to do is ideally pull CO2 out the atmosphere and inject it into the ground. And so the areas that they want to inject it in are near orogenic events like mountain building events. So out west, out in the mountain west. And these areas that we're talking about are going to be where the national parks are, where all of that's at. So this is untapped resources. And that's why, like with this administration, they get very excited about untapped resources.
I have another question. How much is needed? I'm trying to figure out how to frame the question. You said these rare earth elements are needed in like our cell phones and our TVs.
Just
Um,
about everywhere.
Yeah, it's a lot. It's you can't. I you need them like right now.
I mean, is it like, for example, is it like, 1/50th of what is goes into a cell phone, and then you multiply that times,
I
however
don't
many.
know. It's not that much. It's not that much compared to like the other parts, like the glass on your cell phone, um, your chip. It's not that much, but if you add it up over time, it gets big. So like my cell phone, I actually have two cell phones, which is not good as a one's for work. So but I decided to put my mental health first on that one. But if you were to do everybody has a cell phone, then you notice that's how much we have. The best thing, I hate to like harp on this, is to recycle, even though we can do better, we could get better with recycling techniques. When it comes to actual going out and mining it, that's where you're going to have way more consequences. Yes, Dave.
Well, a couple of questions. One is it at all possible? The human race is going to need to continue to extract resources from the planet. Can you envision any way of doing that with minimizing the damage? I mean,
Yeah,
open
so
pit mining is a very destructive way of doing things. There, we've got to find better ways of doing it. But what would you envision? What would you suggest?
I would suggest basically research and development. That's going to be your biggest innovator. And we don't have research and development really going on in the United States right now.
So you mean research and development to reduce the need
Yes, to
for quite
reduce
so
the
much
need.
extraction?
Yeah, yeah, to be more innovative in how to extract this material. Because one thing I didn't talk about is the recovery rates. So the recovery rates for a rare earth element when they go out and they do the open pit mining, it's bad. It's like 20%. And
Hmm.
so it's on the level of oil and gas. So I'm just gonna, if you all know anything about oil and gas, like they go out and they grab the oil and then they might recover by like 20%. And then they'll go back and they'll try to recover another 20%. And so
Hmm.
that's why they just can't take out everything because these things are uh they're trapped in complex silicate structures. And so what a mine will do, they'll go out and they'll recover 20% and they'll go back out and cover. So that's why that mine is staying open. So research and innovation when it comes to recycling and also research and innovation when it goes to if I'm going out to extract it, what is my footprint? Now, are you going to stop an environmental degradation? No, but you can minimize the impact of it through innovation and research. And that's like a mitigation.
Yeah. Well, the my other question was clearly every electric motor is
Yes,
going
yes.
requires magnets and therefore is going to require rare earths.
Yeah.
Um, and electric motors are far better than an internal combustion as far as damage to the environment is concerned.
It
So,
is it is the electric motor. Now I'm not going to try not to sound like a Republican on this one. The electric motor, yes, but the regulation for what you do with that electric motor once it's no longer there, whereas a combustion engine, So here's the thing about CO2 emissions.
Hmm.
CO2 emissions is on the time scale of hundreds of years, tens to hundreds, and
Hmm.
whereas toxic waste and rare earth elements is on the time scale of
Of
millions of
millennia.
years.
Yeah.
Yeah. So
Yeah.
we're talking about, and this is the thing now, this is the thing as a job, like, would I rather have CO2 emissions and deal with that? Or would I rather like, okay, we're going to stop CO2 emissions and we're going to veer towards
But if
really
that
going,
was all we got out of internal combustion, it
right,
wouldn't be so bad. I mean, there's a lot of
exactly,
other crap that comes out,
exactly. And
some of
yeah,
which does have millennial
yes.
implications.
And
So,
we've done an actually really good job of regulating that portion. So like we've done a really good job. Like even though CO2, everybody says CO2 is the worst thing, we've done a great job of sulfur emissions, nitrogen emissions. So we've done that. And then if you're saying to me as a scientist, well, you're just having CO2 and you're just warming up the planet, at least I'm not dealing with really nasty sulfur or nitrogen or the other stuff. So you're right. You do have other things that are coming out, but we know more about it and we clamp down on
oh,
that.
okay.
Yeah, but
Yeah.
I get what you're saying is now we need to clamp down on rare earth elements and like how we're using those.
Okay. And I have one last question, and this deals with electric storage. Recently, I've read some articles on basically an iron redox type battery.
Mhm.
Um, this sounds to me like a great improvement, although it would be quite massive. Do you know
Yes,
anything in that realm?
I do know that now the new source, the new energy source, and that deals with iron, like everybody's going to iron to because iron is the most abundant element on the
Hmm.
planet. And so therefore, you're starting to see with not only in electric energy, they're trying to strip away the hydrogen atom from an iron oxide, but the bad thing about it is we don't know the implications of this because this is really new technology. And also, I'm not trying to say, I know this is not a political thing, but our oligarchs like Bill Gates, Jeff Bezos,
Yeah.
they've already invested in this technology. So
And
they see it as a way of they don't see it as, oh, and then of course when they're going to say, oh, look what we did, but they're going to see it as a greed. It's more of a greed and power
well, that's
situation.
the nature of capitalism.
Yeah, exactly.
That's part of what we have to deal with.
Yeah, so we don't, if
Until we
I were to
find something
go
better.
back and talk about iron, we can have iron like dust, debris, that will be the biggest thing about it. We truly don't know what's going to happen with that,
Okay.
if that technology. But then you're getting away from hydrocarbons. So CO2 emission comes down, but now we have to deal with
Yeah,
the
different.
effects of iron.
Damned if you do, damned if you don't.
Exactly.
Okay. Thanks.
I
Yeah.
think Lisa has a question.
Yeah, thank you. I feel like I'm going to make you repeat a lot of what you just said with David, but a very simplistic framing is for a climate activist, if you say solar is good, but the extractive, rare earth minerals and the social implications and political is bad. Could you do like a simple framing of where urgency comes in? Is it better to eliminate the carbon emissions and pay the price later, or and not just the price of the mining, but like all the people that are involved and all the politics that are involved in exploiting other countries. So, how would you address that?
If I were to address it, number one, I would say like there needs to be a governing body across the world that is actually going to do something, but that's not going to probably happen. You have a governing body that is saying this is how we do it, this is how this is going to be done sustainably, that gets reviewed every 2 years on how to get better at understanding the implications of rare earth elements and how they are being mined. Yeah, you're right. Like right now, our biggest thing is CO2 emissions. So everybody's big on CO2 emissions. let's get that down. But then, like I said, now we're going to have this new problem with rare earth elements. So now it's kind of like, okay, do we just, as a climate activist, are you turning a blind eye to human rights? Are you turning a blind eye to what this is truly doing? Because I always say I don't like being a climate activist. I like being an environmental activist because environment is on the personal scale of somebody's backyard. And so what can we do? Like I said, it's just it has to be a sustainability situation. And then I don't want to say you have to compromise, but what can we do to innovate to push for? So this means that the activists, and one thing that doesn't happen is the scientists and the activists do not talk. Now, if the activists and the scientists start talking, then that's going to make a much, much more better message, and it's going to drive the research into being more sustainable. And so because of that, you're going to need to have innovation from the scientific community that is well funded from government entities or from some entity. And then you're going to have to link that with the climate activists and the environmentalists to say, okay, these are the things that we're concerned with. And then when we're doing these things, not only do we need to understand different ways, but we need to understand them in a sustainable way. So you need to have the pros and the cons. Like you need to fund both sources equally so that way human ingenuity can address that problem of toxic waste. What do we do with uranium that are coming out with these rare earth elements? So what are we doing with pollution effects? And then two, what's going to happen when, unlike CO2 and oil and gas, yes, that's on a that's on a millions of years to replenish, but it's also starting to be replenished now. Rare earth elements, that's on a much, much larger scale. So that's what we have to deal with.
And Jeremy, just I feel like I've heard that you're talking about innovation and research and development, that there's a possibility of other materials besides rare earth materials that can pinch hit for photovoltaic cells and, you know,
Mhm.
devices. Are you?
I know silicon is one of those. Silicon is one. One thing that's good about silicon is abundant. It's not as reactive. The implications are not as big. So that's one thing. I don't know about the other ones. I think iron is the other initiative that you're starting to see. I think so. I'm not too sure, but I didn't get into why rare earth elements are why makes them so unique. Like if you look at the periodic table, they have a different orbital. So because their electrons are in a different orbital, so they can behave differently. So because of that, we use that property to create electronics or to make electronics and MRI and all these other different applications. Yes, Deb.
Oh, I think Matt is next.
Yeah,
Okay.
that's next. Yeah.
Hi, Jeremy. Thank you. That was really informative. A lot of my questions have been answered already, but sort of to extrapolate from some of the previous questions and ideas, I've read that rare earth minerals, and you validated this, are abundant in the United States, but the mining costs are very expensive and it's hard to be sustainable and mitigate the environmental impacts. Can you compare that costs, and I know you're talking about research and development, to mitigate the effects of rare earth mining in the United States against the impacts of going to wars and conflict with other countries to obtain these rare earth minerals, or going to the moon? I understand that there are efforts to even go to the moon. I know that because my niece used to work for a company that did that. I think it was called Interloon or something like that. So I was
Yeah.
just wondering if you can compare, how to mitigate mining. in the United
So
States
yeah,
against other
yeah,
options.
yeah. So it's kind of like, do I want it in my backyard? That's really what I mean, you minus the greed and power situation that we're dealing with. Like I said, I'm sorry that y'all are not political, but minus the greed, minus the greed and power of what you see with this administration that is driven by greed. I want it, mine. It's with wars from United States is more of a energy. I need it. I'm I have a mental illness and I have $1 billion, and then I want to be a trillionaire. I want to be a zillionaire. I just want to hoard everything. Like hoarding is like a mental illness, and we somehow think that rich people are successful and smart when it's really a mental illness that has gone unchecked. But um with that, so that's the situation. This was the situation when it comes to the United States. So if you bring back manufacturing, I don't know if anybody's ever been to China. China's not the best place to go to because you don't see the sun half the time because of all of it would be like what the Industrial Revolution was here. Cloudy, smoky, and then it's like, do I want that in my backyard? No, I don't. But if I have the money to control it and benefit from it, that's where that war is coming from. Now, to address the moon situation, I don't know if anybody ever told you what the moon really is. The moon essentially is planet Earth that got smacked by a meteor and then it ejected out and then it accreted into the moon that surrounds the moon. So the moon itself, if you look at the chemical composition of the moon, it's the exact on Earth. If you look at the chemical composition of the asteroids, it's the exact same thing. So yes, they're trying to go out there. You could go out there, grab it, and then come back. Then you're talking about atmosphere. What are we doing to our atmosphere if we're constantly going out and harnessing things from the moon and then coming back? What does that do to our atmosphere? What does that do to what new things are we bring? Well, what challenges are we now bringing in where we're now accumulating more toxic, we're bringing in toxic radioactivity, even though like it's still like I said, it's the earth, but now that's not a part of the earth's system. You're now bringing it from another body and bringing it in. So now how will we mitigate that process? So that's another thing that is going on. But yes, the moon, yes, they're always trying to do stuff on the moon. I mean, the moon is nothing but your backyard. You can go out, you look at what your backyard is, it's the same thing on the moon.
Okay.
I have
Yeah.
a question.
I think Deb had a question.
Oh, actually, it's was that in answer to Matt's question, Jeremy, that you wanted to like speak more?
About
Were,
uh,
were, were you were about to say something? Was that an answer to Matt's question?
no, I was looking at the chat. Somebody said, does Europe have
Oh,
good regulations? Fred asked that. They have better regulations. One thing about Europe that is very convenient, Europe, is that they don't really have these resources. So it's very convenient for them to have regulations. and and like but they don't care what everybody else is doing.
Not
That's the
the
thing about
Alps?
I'm sorry?
Not the Alps? Don't they have the same kind of older volcanic structure beneath them that would
The
contain these things?
They do, but it's new. It's new and fresh. So it's not like it wouldn't be as abundant as it is on, let's say, China, where like the Alps are still, I mean, the Himalayan mountains are older. They're still forming, but they're older enough where we have those deposits. These Alps are still growing. They're not at that stage yet. Shockingly, but then if you talk about the East African Rift Zone, that's also an area where you have it, but that's also the opening of an ocean and not the creation of a mountain.
Hmm.
Thanks for addressing that. The thought was just if and when global interests want to do the right thing, they might look to Europe. That's what I was asking. So thank you.
Oh, yeah. I agree, and I also think that Europe, I hate to say this, apologies, but it is also driven by, I hate to say it, it's driven by white people, and they're like, okay, we're good over here, but you all over there, yeah, continue what you're doing. So they turn a blind eye to everything that's going on over there. They're like, oh yeah, go ahead and bomb them, do that. We don't care, just don't bring it over here. So that's the thing with Europe.
Yeah.
That's why everybody's like, oh my gosh, they have good regulations. Like, yeah, because they don't also have to deal when they deal with the rest of the world, or just kind of like, just don't be in my space. Kind of like when a white person says, I don't want to talk about racism, I don't see racism. It's that mentality that Europe has when it comes to regulation.
So the regulations are if you're drilling in Europe,
Yeah.
but if you're drilling elsewhere and bringing it to Europe, we're not going to pay attention.
Yeah, that's what Europe does pretty much.
Thank you.
Yes.
That's very Europe of them. It's actually not my question. It's my husband Michael's question.
Hi, Jeremy. First, I want to just thank you for agreeing to be our guest. I mean, I don't think we've had a more informative person talk to us. Your presentation was really, really thorough and well informed, and I really appreciate it. As Jews, my wife was saying, we want to sort of connect, JCAN's mission to like our Jewish values, and we're coming onto the Pesach season. And while you were talking, and as you're still talking, and talking about particularly like the hubris of Europeans, the hubris of Americans, and Western people, and trying to extract these things to save themselves in the mean, but at the same time, sort of killing the planet in just a different way. I'm struck by the story of Moses and striking the rock because he ran out of patience with God to get water for the Israelites. And to me, this is like the exact same situation. We're basically so impatient, our hubris is so high that we're not willing to wait, as you say, for the research and development, and things like that, the better solutions. And so we're going out to get these rare earth elements, or get iron batteries, or probably it's not going to be a good idea either. And even the moon to me seems to be the height of hubris, because the mass of the moon literally, regulates our oceans. If we were to deplete the moon's mass, God knows what the hell would happen, right? So right. It's just absolutely mind-boggling, and it just the lesson of that, that story from Moses hitting the rock and basically screwing himself, and pissing off God. To me, it's like a metaphor to what we're doing. Like, nature is, to me, God's expression of what we're doing wrong. And when you screw with nature, you're going to get punished for your hubris. And I think this is, I think you're pointing out exactly that sort of dynamic in a really great way, like really thorough way. And I appreciate it.
Thank you. Nori, you have your hand up?
Yeah, I want to bring up best management practices, and then I want to ask a question about manganese. So when I worked in coal geology, it was really interesting to watch that Bureau of Mines and EPA, this was under Clinton Gore, they really started making an issue about BMPs, about best management practices, and EPA was giving awards to the very few companies, people who were actually, individual humans actually, who actually cared. But that's exactly the question that you're asking, is how do we force best management practices? Because we're not going to give up mining. We're geologists. We're not giving up mining, and we're not giving up extraction, but we certainly can be on the side of pushing for best management practices. So that was the one thing I wanted to bring up. I want to ask a question about manganese. I know that manganese mixed with iron makes steel. Okay. So I've been reading what the rare earths are, and I see that manganese does get included in the list. Does it get included because it's being used, or does it get included because manganese nodules have iron, have nickel and cobalt?
Yeah, so manganese nodules, they are one of the sources of it. And so, yes, they're manganese nodules. I don't want to go into detail about it, but basically, back in the day when the ocean was forming, we had something happens where we had this iron event where iron is just kind of like all over the ocean, and then it kind of generates productivity somehow. And then we had these nodules just everywhere. So those nodules are just, you can find a nodule in your, if your property used to be ocean, you could probably dig and find a nodule. So these nodules, they range in size. They could be as small as this. They could be as big as your house. And they're actually really, really good sources of rare earth elements because they are enriched in rare earth elements. And that has to do with the geology, it has to do with the environment of forming manganese nodules and the absorption effect that they have with rare earth elements. So they just absorb, and then they, like the ions that were in the ocean were just absorbing, and then they're included in this structure of a manganese nodule. So that's one of the big things. And then when you talk about I showed the picture of like the seafloor being covered with nodules. Yeah, those are the iron manganese. So you'll hear people say iron manganese nodules, manganese nodules. They're pretty much, is the body of it is an iron or manganese body that has these rare earth elements in them.
Is manganese being used?
It
Do you know?
it's being used, but it's not one of those. Yes, it is being used. Like we go out and we use manganese, like that is, but manganese is not a
Not a rare.
is not rare. When it comes, every, like almost every country has manganese, and we have mines everywhere, so that's not a big problem. But we don't have manganese nodules everywhere because some people consider manganese as one of the major elements of the continental crust. So it's everywhere. It's plentiful. Yes, it is being used. It is used in superalloys. It is used in
Uh,
defense, everything. So there is a purpose for it, but it's not one of those things that's a dire thing. Like we're not, oh my gosh, we're running out of manganese. Like that's not one thing that people are concerned with.
got it. I'll give you an image, okay? The manganese nodules are sitting at the redox boundary, so it has to do
Yes, they
with
are.
the difference between when the ocean was oxygenated above and deoxygenated below. And then I'll give you one more little picture of it, and that is the microbial issue, and that is the bacteria who are concentrating the metals because of proteins that they have in their waste products, which sticks those metals into the manganese nodules. So
Yes, you are absolutely right.
a part of this story for you.
Yeah, you're absolutely right. Now you're jogging my memory back because one thing that we do see with mass extinction events are these manganese iron layers.
Exactly, redox
Yeah,
boundaries.
redox boundaries, and then so like redox, and then sulfuric or acidic oceans, all that kind of stuff from that was
Thanks.
pretty, yeah, driven by volcanic activity. But yeah, now you take me back to my PhD. I had to like go and dive deep back into my brain. Thank you for that. But yes, you're absolutely right.
Sure.
Okay. Well, all right, guys, there is a test tomorrow that we're going to be distributing so everybody can review these notes. Thank you so much, Jeremy. This is like, in case you didn't know, we're just like secretly a big crowd of nerds. So this was like, like probably the best thing we've done in like 5 years. So thank you so much. This has been like, I think we're all probably going to like be talking about this for a little while. Expect emails. We're going to be distributing Jeremy's presentation as well as his source list. I'm still thinking about radioactivity. If you guys are into this, please join us next week at lunch at 1 o'clock when Jerry McGovern is going to be talking about his book, and Jeremy might have a slightly more optimistic view of all of these issues than he does. Just fair warning. But Jeremy, thank you again. This was fantastic, and yeah, we'll be in touch.
Yeah. Thank you.
Thank you very much.
For having me. All right. Bye.
Bye.